Thank you. Good afternoon, and I want to start by saying it's a great privilege to be here. I thank the organizers for trusting that this will not be a wasted hour. Also, congratulations on the anniversaries of the 29th birthday of Dean Tsuboi and Steve Herder. And congratulations to everyone resident here for the 2020 Olympiad, which will take place in Tokyo. Everything I will talk about is joint work with Patrick Foulon, who has been previously mentioned, but who is not here. This means that the good ideas are his and the mistakes are mine. And Steve, since you're conveniently in back, it's your job to remind me if I get too small on the chalkboard. The subjects, both of which I want to talk about, actually were, in a manner of speaking, both started by Yoshi Mitsumatsu 30 years ago in 1983 in a paper that was published in 1985. And Etienne Gis just reminded me that, in fact, for him, that was a start into one of the subjects I want to start with today. This paper contained a rather astonishing and remarkable statement. It was a theorem that said either the Godbillon-Vey class is not a topological invariant, or a geodesic flow of a surface, this C2 stable and unstable foliations, must come from a hyperbolic metric. This is a rather remarkable statement, and it certainly got Etienne Gis's attention. And for me, the prehistory of this starts just around that time when my doctoral advisor, Anatole Katok, and Steve Herder were working on a paper entitled Differentiability, Rigidity, and Godbillon-Vey Classes for Anosov Flows. And their work, together with work that Etienne Gis undertook, provides a great starting point. Let me note these names. I'll get more specific about statements in due course. But in particular, these two taken together, as far as Yoshi Mitsumatsu's question went, or rather dichotomy went, established that indeed you have the desired conclusion. If you have a geodesic flow of a surface and it's anosov, meaning negative curvature, and it has C2 foliations, then it is indeed algebraic. The surface must be hyperbolic. Well, rather soon after, the real foundation to a whole industry of rigidity was laid by Masahiko Kanai, who actually went straight to arbitrary dimension with a similar statement. And in keeping with the theme of this workshop, I should point out that that paper of his was dedicated to Professor Morio Obata on his 60th birthday. This paper by Kanai proved something that justified the following conjecture by Kanai, which is that if you have a geodesic flow, and whenever I forget to say it, I usually mean in negative curvature, and I will do Riemannian manifolds, whose anosov splitting, which you have for hyperbolic flows such as these. Let me say C2, that was a conjecture at the time. When the anosov splitting is C2, then these flows are isomorphic, meaning actually smoothly conjugate. To the geodesic flow of a locally symmetric space. This was in my early graduate student days, and Masahiko came to Caltech for a few years, and that started a race in which Katok and Renato Ferres, a fellow graduate student of mine, was involved. Let me pause for a moment for a message from our sponsor, as it were, to introduce some of the notions and then go on to where this story continues. An Anosov diffeomorphism, and for the moment it is a diffeomorphism, is a diffeomorphism of a differentiable, of a smooth manifold, such that the tangent bundle of this manifold splits into two subbundles, ES and EU, or E plus and E minus, an expanding one and a contracting one, where we see exponential rates as we iterate the diffeomorphism. A good example is provided by the diffeomorphism of the 2 torus R2 mod Z2 that's induced by this linear map on the plane. In fact, that is the classical example. And the local picture can be drawn like this, that we have expanding and contracting directions. And actually, one thing that you see in this local picture makes for a good criterion that helps verify this condition here of having an expanding and contraction direction without actually having to find them. And that is an invariant cone criterion. If I draw a sector like this here, meaning I've meant to draw this region right here, and I apply my Anosov diffeomorphism, because I'm stretching this way and compressing that way, I will get a smaller cone after applying my diffeomorphism. And one can make that the defining property together with the fact that things expand inside these cones. For this picture, I'm pretending that the point is a fixed point, but one can define this in terms of cone families. One pertinent thing is, for the price of this example, you get many examples, because if you take an Anosov diffeomorphism and make a C1 perturbation, you get another one. However, it's not profoundly different in that you have topological rigidity. If I take, for instance, this thing and I make a C1 perturbation, the new thing I get is up to homeomorphism, up to continuous change of variables, the same thing anyway. In particular, it actually, not in particular, but even more so, it turns out that diffeomorphisms of this type, so far as they're known, are in fact given simply by a list of linear examples on tori, as well as slightly more complicated linear examples on nil manifolds or infranil manifolds. So there aren't a lot of them once you mod out by topological conjugacy. The situation is different for flows. Here, the tangent bundle is again going to split into these directions, except, of course, we also have necessarily a flow direction. And happily, Professor Minakawa earlier today gave a nice summary of some pertinent things about Anosov flows. One dichotomy that goes a long way in understanding these is to think on one hand about suspensions, on the other hand about geodesic flows, which are very far from being suspensions. But unlike in the case of Anosov diffeomorphisms, where I was just telling you that there aren't more examples than what one might deem the obvious ones, in this context, there are other ones. Professor Minakawa mentioned the Bonatti-Langevin examples. There are other ones beyond that as well. So among the authors that cooked up new kinds of examples were Franks and Williams. This is an example of a collection of examples of Anosov flows that are not transitive. There is no known example of an Anosov diffeomorphism that isn't. Examples by Handel and Thurston, on which I will comment briefly, in fact, somewhat extensively down the line. inspired by them Sue Goodman, Thierry Barbeau, more recently, and like I said, this is a bit out of order. Bonatti and Langevin had some interesting ones as well that inspired some of the work I happen to put on the same list somewhere higher up. Good. One picture I will draw is the Handel and Thurston example, or surgery construction, because this is in fact closely related to the first subject I want to talk about. What they're looking at is a surface like this, and they take the geodesic flow on that surface as a starting point. And they think about cutting the surface into two pieces by taking the geodesic that goes around here. So you can think about this surface as having one Handel and one Thurston. Bad joke, sorry. The surgery they want to perform is not going to be performed on the surface. The flow that we're talking about is initially the geodesic flow on the surface, taken to have curvature negative everywhere despite the picture. And so it takes place in the unit tangent bundle. One can restrict here to unit vectors when one looks at geodesic flows. And I'll augment the picture in order to show where the surgery is being performed. In the unit tangent bundle, we look at the circle. The corresponding geodesic is actually the tangent vectors along that closed curve here. So in fact, there is a torus inside the unit tangent bundle here on which one can perform surgery. It's this circle cross the circle of unit tangent vectors to each one of its points. That's a torus sitting inside S1M, a two torus. And one can think about something, and that's what Patrick and I actually do. If I take this vector here, and in fact, the vector is orthogonal to the geodesic all along this geodesic. So far, I just have a circle. I can think about small variations of these. So I'm looking at an interval of vectors, all of which are safely transverse to the tangent vector field here. What that gives us is an annulus, and that one is transverse to the flow, because I've made sure that I have more or less 90-degree angle with the actual flow, which would be going round and round and round this thing, this way or that way, either way, transverse to what we have here. So that's a surgery annulus. One way of drawing it is like this. There is an annulus, and the surgery construction identifies this annulus with a like annulus, except that this sample line here is deformed to something, actually it doesn't matter which way around, that if you think about repeating periodically or going behind the blackboard to the next street over, it winds around once or 17 times, however many times you want. So that is a way of defining a so-called Dehn surgery in this three-manifold. And that's what they do. And that gives them an example of a new flow, and they work somewhat hard to establish that the new flow is still an Anossov flow, because if it weren't, it wouldn't be as interesting. Let me return then to the story that I started here, now that we have seen that for Anossov flows, there is a much bigger zoo than the standard examples, as is the case with Anossov diffeomorphisms, at least so far as we know. So Masahiko Kanai's seminal work that I mentioned here is an arbitrary dimension and started with manifolds with a strong pinching condition on the curvature so that the available locally symmetric spaces under those assumptions were constantly curved. And the obvious thing one wants to do is go beyond that and establish more generally that smooth invariant foliations imply that the metric is a locally symmetric one, as Masahiko indeed conjectured. And this is something that was picked up by Katoka and Ferres. They looked for other manifolds on which they could prove Kanai's theorem. The hope being that eventually they would have conditions under which every possible locally symmetric space, the type of every one of them, was covered by their theorems. I remember those days. There was a strong competitive spirit here, and there was a race going on with a group in France consisting of Benoit, Yves Benoit, Patrick Foulon, and François Laborie. And, all right, they won. What they proved is that if you take any contact annals of flow, that has smooth invariant foliations, corresponds to locally symmetric space, meaning is actually smoothly, not just topologically, but smoothly conjugate to the geodesic flow of a locally symmetric space, or more specifically to the geodesic flow of a Riemannian metric on a manifold which is locally symmetric. So in particular, that covers all possible manifolds, which my friends Anatol Katok and Hato Ferris were trying to pick off one at a time. They're all included in here. What I didn't fully appreciate at that time was they don't only include all the manifolds, they include flows about which we don't even know that they have the structure of a geodesic flow at all. Just a contact structure and the Anosov property and nothing more. And out of smooth foliations, they managed to get somehow the structure of a geodesic flow. That is actually quite a remarkable thing. And in fact, that was a really hard thing about what they were doing. And it's no coincidence that the work I'm reporting on is with Patrick Foulon, because in the days that they were working on this result and struggling mightily to actually, out of contact Anosov with smooth foliations, getting the structure of a geodesic flow, he kept wondering, does it really have to be this hard? Because it was very hard. So as they were working, the question was simply, can one get the geodesic flow structure simply out of contact Anosov? And that's in a way inspired by the dichotomy on the top board there, that thinking about suspensions on the one hand, geodesic flows on the other goes a long way of thinking about all Anosov flows. Contact means it's definitely not a suspension. So it ought to be a geodesic flow. However, given that if you don't have contact, there's all this other stuff around, the question arises, does contact get you there? The short version of the first part of the talk is a two-letter theorem that says, no, you can't. The contact structure alone does not do it. And so the first thing I want to talk about here is simply a construction that produces funky examples like the ones I listed there, some of them, but among contact Anosov flows. In other words, that these constructions here can be done so as to yield contact flows, and that shows that contact alone does not get you where you need to be. There's something really deep about the smoothness of the invariant foliations that's needed to get this magical theorem by Benoit, Foulon, and Laborie. Good. Let me state that result with a view to foliation, since this is hopefully what makes the audience as happy as possible. So the theorem that in short says no could be framed in terms of foliations as in saying the following, that we produce contact three manifolds with foliations that are C1 plus big Sigmund. You might as well say C1 plus a tad. That's good enough for this. The foliations are Lagrangian, meaning tangent to the kernel of the contact form and a maximal dimension. And they arise as stable, unstable foliations of another flows that are weird. And in particular, they are topologically different from any of the usual algebraic examples. In particular, also in terms of foliations, they're not topologically equivalent to any volume-preserving Anasa flow with nice foliations. Okay, I told Steve to tell me when I'm getting too small. This is intentionally small. This is Sigmund written in very small letters. This is a C1 plus little Sigmund condition. This is, right, so you can put a C2 there actually and get a hopefully interesting and correct conclusion. Yes. Right, so this is one way of talking mostly about foliations and saying what we produce in that respect. So what we do produce are foliations that can be made nicer in a way that carries the dynamics at the same time. No topological conjugacy here. For those of you who are interested more in the dynamics and the foliations, there are other interesting things one can say about these flows, among them being that for the flows that we construct, the Bowen-Margulis measure of maximal entropy is singular, no matter what you do. In fact, it's singular for everything topologically conjugate to it. Put differently, the measure of theoretic entropy is going to be different from the topological entropy when you take the natural measure that you have for the contact structure. Good. Just for fun, let me digress, by the way, to say that less than some 20 years ago, I guess, Dean Tsuboi actually had a paper about regular projective Anasa flows on Seifert 3 manifolds, showing that they turn out to have to be Anasa flows. Among the things we do with our surgeries, we definitely break a Seifert structure. Manifolds we get. In fact, the surgery that we do here is more general, but it subsumes the Handel-Thurston surgery. Doing that kind of thing over there really breaks the bundle structure that makes this unitangent bundle. That's among the things that makes these flows so different from what they might otherwise be. Now, the question, of course, is just where the novelty resides, given that exotic examples have been known. And of course, it resides in the fact that I say contact in many places. And so the central idea that we have here is to look at the surgery of Handel and Thurston and others and think of doing it in such a way that when you're done, having started from a contact flow, you still have a contact flow afterwards. Since I want to give some time for the second subject, I won't actually talk very much about the ingredients for making sure that that's what actually happens. It's mostly carrying out the surgery with some proper care, choosing for local parameterizations a flow box, first of all. That secondly has a Darboux property, which means that a contact form looks really canonical, like the standard R3 contact form that you might pick. Then we do the surgery, and actually turns out that breaks the contact form. So we take a closer look at how it's broken, and it turns out there's a clever way of fixing it to a contact form that's a deformed original, but behaves nicely under the surgery. So you still have a contact form, except the new flow that you construct by surgery may not preserve this new contact flow form. Happily, you can change the behavior relative to a contact form, often by changing time a little bit. Like when you hit a bump in the road or you see it coming, you hit the brakes. Well, if you do that just right, you can make the new flow preserve the new contact form. That's the essential thing. So topologically, what we do is not new. What is new is that one can actually make sure to do what our predecessors have done with enough care to salvage the contact structure throughout the process, or rather rebuild it at the end. Good. Now, this is work that is happily complete. In fact, I might have to apologize because after I announced my intent to talk about this, in fact did get published. So you can look it up in Geometry and Topology, a recent issue, which hopefully means that it's correct. Now, the other thing I wanted to talk about, hopefully to the delight of those who care, is about Godbillon-Vey classes. And you have a right to expect that the things I talk about are new, or true, or interesting, preferably all three. And this is very much a work in progress, so I can guarantee none of these three. But I think this is a great audience which to bring up such early work, because I might get feedback on it being either not new or not true, maybe not interesting, or none, whatever. Good. Maybe I will start this over here. And like I said, this is very much in progress. Again, with Patrick Foulon. And again, this term itself I saw first in this paper by Steve Hurd and Anatol Katok. And that paper actually influenced much of my early career in a really deep way. But again, I mentioned previous to that, Mitsumatsu started this all. In fact, Tsuboi has made some interesting contributions as well, the characterization of the Godbillon-Vey invariant that is really interesting, and in turn inspired by the Hurd and Katok paper and having to do with regularity, which is an issue that is behind several of the things I've talked about already. Another question that those of you might have who are not already experts is, what do Godbillon-Vey classes actually mean? Well, if you have that question, you're in the right place. I recommend that you buy dinner for either Steve Herder or Takashi Tsuboi or Etienne or someone else, and you can get the best possible illumination on the subject, more so than I can do. Good. Our hope is that we have something that's a moderately new idea in that context. The context is a bit more restrictive than the original notion. We want to look at Anosov flows and the invariant foliations for this flow, and for those look at how one can possibly define Godbillon-Vey invariance possibly. And as before, we want it to be contact. That gives us a structure that gives a starting handle on this. So we look at a contact Anosov flow. So we have the splitting, as I mentioned before, into this, and one more thing. So the overall splitting is going to be an A plus, an Rx, and an E minus. Contact means, now I'll be explicit so we can play around with formulas, that X being the vector field that generates the flow gives 1 on the contact form. I can, in this context, assume or choose my contact form to vanish on the other two. And if I stick the vector field into dA, I get 0, provided that the other stuff I stick in there is one or the other of these. So that's none of these is deep. That's just the kind of thing you can do. And if you stick to not mixing expansion and contraction, then dA necessarily has to be 0. Interestingly, by the way, these things are pretty obvious, but they do tie in with ideas that were really central to Kanai's work, which is in fact the very technical points that were developed by Ferris and Katok as they were trying to push further. And I'm going to write down a definition with some undefined symbols, which I will then define, so you can get some idea of where this is coming from. All right, so GV is going to stand for Godbillon-Vey, and the proposed definition involves a number of things. With index 0, I'm going to do something that's not much of a definition. It's just the volume of the manifold, but it fits into a pattern that I'll presently continue. We will have an odd dimensional manifold where the expanding contracting subspace have the same dimension. I'll call it M. That's the same M as here to make the dimension right altogether. Here's the next one. I replace my A, the contact form, by another one form, which I'll presently have to give to you. But for now, that's my first class. Then there is a second one where I not only do that, but I replace one of the dAs by d beta. And I think now you can see how I'm going to go on. I'm just going to replace one by one yet another dA by another d beta. So I'm going to keep going until, in the end, with m plus 1, there are no more a's left. That's our proposed definition, which of course makes no sense until I'll tell you what beta is supposed to be. So to define beta, yes. Beta is defined implicitly by a formula like this, where I've replaced the beta that was previously undefined by something new that's now undefined, so I have to tell you that as well. Alpha is something that vanishes on this thingy here, and if you feel like it, you can replace minuses by pluses and vice versa to get it the other way around. And moreover, what makes alpha interesting is that when you look at the complementary thing, you get a volume out of A. So I think of this as an unstable volume, but in the sense of having an M form that's defined everywhere, it's just restricted to unstable, I get a volume. I should note that this happens to define beta uniquely, well, not totally, but on the expanding space. Contracting, rather. Sorry, contracting. Good. So I guess the first lemma one should prove whenever doing something of the sort is that this definition is actually meaningful and that this is a well-defined object, given that I have choices. If I have my A of this type, there's still a bit of tinkering I can do with beta. Not here, but on the complementary subspace I could do pretty much whatever. So I'd like to show that whatever choice I make for beta given the rest are not going to change those things over there. Takes a bit of doing, but okay. Actually, the other thing too is, of course, I could choose an unstable volume in a variety of different ways because I have no particular requirements in it, just that it be an unstable volume, which means that's really only defined up to a positive function. If I change my alpha by replacing with e2 some function times alpha, it turns out that the effect here is that I want beta plus df, where f is a function in the exponent. So the first lemma would be if I look at every one of these formulas and replace my beta by beta plus a df, that doesn't change anything. Turns out it doesn't. Well, here pretty obviously it doesn't. Bit of work here, but it's trivial actually because the difference is integrating a closed form over the manifold, and that is nothing. The slightly harder thing is, again, to show that the non-uniqueness in beta, given a choice of alpha, doesn't make a huge difference. Good. So I made the obvious remark. Well, this one's well defined, by the way, just in case you want to hear unsurprising news. It is the volume. It just happens to be a natural first thing in the series, fittingly with subscript 0. one thing that is moderately novel maybe in this context is the first one. Okay, so GV sub 1 is, well, not the usual Godbillon-Vey class. It turns out to be the volume entropy. Liouville in the sense of the contact form defines a volume, its entropy, as in measured theoretic entropy, turns out to be GV1. That actually turns out to be not rocket science. I want to prove this. Exactly, that's precisely it. So let me just, instead of writing down lots of formulas that are going to lose you, after a bit of computation, what one can show is exactly that, which is that beta applied to the vector field generating the flow is exactly the change in volume that we get when moving in this direction. So beta indeed does measure the infinitesimal expansion of volume. Okay, so why is that interesting? Ah, yes, because when we go over here and start integrating away, what we're effectively doing is that we're integrating over the entire manifold, meaning we're taking a space average of the volume expansion rate. Contact flows being ergodic, that's the same as taking the time average of a corresponding expression, which is the sum of the positively up-bound exponents. And the pace and entropy formula tells you, well, that's exactly your measured theoretic entropy for the measure you're looking at. So it turns out that using those ingredients, it's really just a matter of futzing around a little bit with these formulas to see that this is what happens. So that's not a deep result, just sort of amusing that it tells you at least that this is something that carries at least some modicum of meaning. So this carries meaning which isn't profound, but so it doesn't justify giving a name except for the list. There is something here that's of some interest. The final thing we can prove about this list is that if you look at this, GV2, in the context of, notice this was m-dimensional, but if we restrict attention to where we started, geodesic flows on surfaces of negative curvature, then this turns out to be the thing that puts a G and a V here. When we do this for geodesic flows on negatively curved surfaces, this here is the usual Godbillon-Vey invariant for the foliation we're looking at, and we prove that by producing the Mitsumatsu formula for that very thing out of this definition. So that is a proposition that makes it interesting and justifies why I brought in the names of Godbillon and Vey. So this is the other proposition. And that says that GV2 is what you would call, in this room especially, the usual Godbillon-Vey invariant for geodesic flows on negatively curved surfaces. And again, happily, there is a ready-made formula by Mitsumatsu, and for those who didn't read those papers, aren't into GV, happily, the lecture by Ruggiero earlier on mentioned that formula, so let's refer to that. So having verified that it's a real deal, we can say, okay, GV2 is the usual Godbillon-Vey invariant. GV1 fits, interpolates between that and volume if you want to write things down in this fashion. And in higher dimension, you could write down further ones, except you still have to figure out whether they're interesting or have any particular meaning that goes beyond what they are. So there is a story as it goes so far. I should say one more thing, which is that so far the definitions And some of the calculations that go into even that it's well defined and the like are easiest to do when we assume that the invariant foliations are C2, which, as those who have listened to early on realize, is rather restrictive because that pretty much tells you that the systems you're looking at are pretty standard classical examples. So in fact, the core of this project is what we're planning for this year, which is to get rid of the two assumption and make this work for assumptions that don't imply known rigidity results. You don't have to go much below C2 to make that true, and we have pretty clear ideas of how to do it. So it's not like this is pie in the sky. Here we have something that works that I think is going to get there. The question that I cannot answer, but others for whom you can buy dinner will, and I hope they'll let me know, is whether this is interesting, and assuming that it's interesting, whether this is new. Once again, I want to thank everyone for the attention and the organizers for inviting me and a fabulous conference. Thank you. I was hoping Steve would speak up.
Oh, you know I'd speak up. Now, I think, now this is actually a question for all of our folks who will be on here, and actually also Matt. I think there was a paper by Musoon, or possibly Lehman in the middle 70s, where they introduced this kind of filtered Godbillon-Vey class. They didn't interpret it, and certainly they had zero examples. But this is the kind of spectral sequence game that people played in the mid-70s. Does anybody remember that paper? That's the only reference I would come up with for this. Because you're walking down the terms of the ET spectral sequence.
Mm.
But you have examples, and in the 70s, people just did every piece of algebra.
Well, that's, thank you, yeah.
I think the other thing I remember is somebody talked about higher moments. Your GB1 is like a first moment class, and then there's some other paper that talks about the higher moments. I would have pointed at Yoshi down here. I thought it was in his paper. No?
Talk about putting the organizers on the spot. Well, thank you, Steve. I'll try to ferret out that reference from the 70s about the sequence. Excellent. Thank you. I'm going to be wintering in Marseille. I wasn't planning to advertise this, but since you put me up to this, I'll be with Patrick Foulon and colleagues from November through April. I recommend that for winter. Try to stay away from Monte Carlo. Well, it's still going. Yes. I just have it here because it's sort of adorable to be sharp. It really is. I don't really need it. So, in this case, they are, because they are contact on 3 manifolds, volume preserving on 3 manifolds. So there's only one thing you can do. In fact, you prove that they are. So exactly, this is not new. So what I could say here is C1 or anything. The main point being that it's, like you said here, actually not topologically the same as anything C2. It just happens that thanks to, you should read it sometime, the work by Herder and Katok. This is as sharp as it really gets in that context, and so you can't go from here to there. But in particular, you can't go to C infinity here or C2. There's just something you cannot do because topologically this is just a fundamentally different type. And again, this is just a restatement of the familiar fact in that context that when you have C2, or thanks to you and Etienne, C1 plus little sigmund, then you have a smooth conjugacy to a standard algebraic thing and the like, in particular topological one. And ours, simply because by surgery we break the topology, is not even topologically of the same type, therefore not smoothly, and therefore it can't be good enough for those theorems. That's all there is to it.
So in the abstract, you have a rigidity statement for surfaces and panels and flows. But in here, you're able to recover the Hubble entropy with GD1. Do you think you get a rigidity statement for geodesic flows in locally symmetric spaces of higher rank, or sorry, rank 1 with high dimension, like what this one would provide?
I don't know, but it's quite possible. So far what we've done is picked some low-hanging fruit. It happened to be fairly easy to do with things that are known to be around. It's an interesting question because in fact that's sort of the kind of thing one should be fishing for. On the other hand, just in case you're interested, we haven't investigated that enough that you can't go and try it for yourself and see what you can get out of this. So feel free to do that. But it's definitely, so one thing I didn't mention, but like you noticed, is in the abstract. It's not just that we have an interpretation, but for instance, by a bit of massaging them together, with a proof that's really as simple as the Cauchy-Schwarz inequality, we can actually reproduce non-rigidity results of the Hurdy-Kartokrogi's type, which is adorable. But we have not pursued that in higher dimension for the high-tech stuff. That'll be really nifty. At this point, I don't have any opinion as to what probability of success I'd give it. But it's a nice idea. Well, not in the sense that we can classify them or give limits on how many there are. I can tell you a bit about the surgery. The way we produce them is we start from a manifold with a contact flow on it, which might already be one of these weird ones, but in particular it could be that construction right here, but not necessarily with a waste. It could be, in fact, any closed geodesic on there. In particular, for instance, if instead of doing the little red separating geodesic, we take a knot in the unit tangent bundle that projects to a filling geodesic. A Folk-Law theorem is that the complement of that knot in S1 is a hyperbolic manifold, which means that when we do our surgery, I said you can spin around 1 time, 2 times, 17 times. Well, except for finite many times, most of these will actually give you hyperbolic manifolds. So it's using a Folk-Law theorem, which we actually produced in the paper. I owe thanks to Sergio Fenley, among others, for making that work. But in particular, once we start with something contact anosov, whether we want hyperbolic or not, we do these Dane-like surgeries, and basically for every positive integer, the thing we do is going to give you one of these new examples. And so you're really limited by where do you want to start in terms of contact anosov flow and which knot in it, and then go ahead and do your surgery and you'll get lots of different things coming out. So a countable family out of every starting point. So there's a lot of things that you get that are of this different type. So it's not just 1 or 2, it's a ton.